All right, so let's talk about example 3.4, and this is going to be an example of an integral balance. So these have a different format than most of our balances. So most of what we see will be a differential balance, but this is an example of an integral balance. So let's take a look at what's going on in the system. So we're bubbling air through a tank of liquid hexane at a specific molar rate. So right away, we know this is an N with a dot over the top of it. We have a gas stream leaving the tank with a specific amount of moles. So there's a Y that we might need in the system. And air can be considered insoluble in liquid hexane. We'll need that at some point to think about the general balance equation. And then we want to use an integral balance to estimate the time required to vaporize a specific volume of liquid. So there's a volume, there's a time. Okay, we haven't dealt with time or volumes of things yet. I'm going to refocus my camera for you. 1 second here. There we go. So we'll take a look at this. First things first, number one step is always to draw our flow diagram. So this is the setup video. So we've got some kind of a tank, and inside of that tank, we have liquid hexane. So hexane, if you go look it up, is C6H4. Okay. And we are going to put little bubbles of air. And what we're trying to do is bubble something out of the top. So we're pushing bubbles in through the bottom with some air. Okay. So we're only adding air to the system. This is what's coming in. So I'm going to call this a 1. And then we have a gas stream that's leaving the tank, and I'm going to call that 2. So we have 1 input, 1 output. Okay. So in our input specifically, we're only adding air to the system. So I'm just going to use n dot air in 1 as that rate. Okay. And we're actually given that number. It's the 0.1 kilomoles per minute. So I'm going to add that onto my diagram. Kilomoles per minute. Okay. Now this stream in, does this have any hexane? Well, according to the problem, no, it's just pushing air in. So down here, we would know that Y of air in our first stream is equal to 1, and the Y of hexane in this stream is equal to 0. Okay, so in this particular problem, I'm actually using the chemical formulas as my subscripts. I could use an A for air and an H for hexane if I wanted to make it easier. But notice that there's air coming in, there's something happening here, right? And then we're bubbling something out the top. Okay, so the gas stream that's leaving, this is going to be a combination of air and hexane. And we know, based on what the problem tells us, that we have a mole fraction of hexane vapor in 2 equal to 0.1. Okay? 10%. Okay? The rest of this gas must be air. So we know that Y of air in 2 is 100% minus that 10%, which gives us 90% air coming out. Okay, so we know that. Now, this is a weird different problem, right? Because we're using an integral balance and we're trying to vaporize a certain amount. So there's going to be, right inside here, there's going to be a change in volume. And that change in volume is that 10 cubic meters of liquid. We're losing 10 of that. So that's a delta right here, a change. Okay. And before we go anything, let's think about what is going to be our strategy to do this. Well, we have time and we have volume. How are those two related? We know how they're related, right? There's a way that we can relate those two. Well, let's take a look at units. What if we have volume in a specific amount of time? Volume itself has meters cubed as its units. Time might be seconds, might be minutes, right? That is a rate. So that's a volumetric flow rate. So in an integral balance, we're not actually doing integrals. We're just thinking a little bit more about what a volumetric flow actually is. So if we think about this and we have a total volume here, right? We want to know the time. Well, we could probably find this volumetric flow rate leaving the system, right? We could probably find that change. And that change in V, this is related to an accumulation. And it's a negative accumulation. It's a loss of material. So this is not a steady state system, right? So because there's a change in volume in a specific amount of time, there has to be a volumetric flow that's leaving, and that's going to be related to this flow out of the system. So there's some flow that's leaving the system, and we know that there's at least a molar flow out. So let's call that N2, right? And that N2 is somehow going to be related to this volume here. So we could say volume 2 here. So the strategy for this problem is to think about finding this volumetric flow, because if we have this volumetric flow, we can find this time because we know the change in volume. So we're trying to find this volume flow, which means that we'll probably need to know mass flow because mass is related to volume by density. So we need to go from N to M to V in order to solve this problem. Okay? So to finish setting up this problem, let's think about what balances we could write, right? So how many balances could we write? Well, there are 3 balances. The first is the one we can always write. It's the overall balance. The whole system, right? Just the numbers, not the letters. We can also write a balance on air, and we can also write a balance on hexane in our system. Okay, so we can write 3 different balances. So let's do that. Let's write the overall balance. Okay, so look at the overall system. We always start with the general balance equation. So input minus output plus generation minus consumption equals accumulation. Okay, now here's where things start to get a little bit tricky in this particular problem. When we balance things overall and we balance things by species, different things are going to happen. So let's go look at the overall system. In the overall system, the components of air and what comes out of the system, right? Are there any generation or consumption? Is there any reaction that's happening in here? And the answer to that is no. We're just doing physical processes, not reactions. We're bubbling air through a liquid, but they are not interacting. And that's what this line up here is also helping us find out. Air is insoluble in liquid hexane, right? So that means that air is not going to dissolve into this hexane. So that means there's no chemical reactions that's going to occur. So this line right here is telling us that generation equals 0 and consumption equals 0 with this type of problem. So we know for sure that we can get rid of generation and consumption. Okay? The question now becomes, is this steady state and can we get rid of accumulation? Well, I'm not 100% sure about that, right? So maybe we need to just leave this right now, right here. So let's just leave that for the moment, okay? Next, let's do a balance on hexane. We start with the same equation. I minus O plus G minus C equals A. And then let's think about this. Okay, same thing. Air and hexane are insoluble, so we can definitely get rid of generation and consumption. I'm not 100% sure about accumulation yet. There's definitely hexane in the output, right? We know that it's 10% hexane vapor. But is there hexane in the input? Well, no, there's not, because it's just air. So we know there's actually no hexane in the input. So check it out. That can actually go to 0. And so what we find for hexane is that the negative output is going to be equal to the accumulation. So we know accumulation must be negative, which makes sense if you think about it, right? Because if we go up here, we're losing hexane in this system. So the whatever's leaving the output is what we're losing inside here, which makes sense because you can't create or destroy hexane. All right, last one is to do a balance on air. All right, so start with the same thing. Input minus output plus generation minus consumption equals accumulation. Air is still insoluble in hexane, so let's get rid of generation, let's get rid of consumption. Can we get rid of accumulation in this particular instance? Well, if we look at just the air component of this system, air itself is actually in steady state. It's hard to kind of tell from this system, but you're always feeding at the same rate and there's always a certain amount coming out. There's no air that accumulates in this system, it comes right back out. So the amount of air that's going in should theoretically be related to the amount of air that's going out. So as a result, air is actually in steady state, but the overall system is not. So in this case, for air, we would say that the input equals the output. And so what I want you to take away from this is look at the overall balance. It has three terms, right? So if we're looking at everything in the system, there are three things happening. But with hexane, there's only two of those terms, and with air, there's only two of those terms. But between air and hexane, we cover all the terms in the overall balance. So that's going to be really critical. So what's going to want to happen during the semester is you're going to want to say, I'm just going to do the overall balance. Here's my equation. Let's go. But it's different for every species. We have to look at each different scenario. And that's really, really critical about this problem. That's going to be it for setup. We are going to take the setup and we are going to solve this problem in the next video.